Okay, so welcome everybody to Tuesday morning session. Just before we start the first talk, let me recall to the speakers that if you agree to it, we would like you to send the talk of the PDF of your presentation, in case you gave a computer presentation, to Yvan Bardet. His email address is here. I also recall you that you're supposed to bring your ID or your passport for the cocktail dinner tonight. Okay, so the first speaker is Vern Paulsen, who will speak about C-star algebras and synchronous games.
Thank you. Okay, well, I'd like to thank the organizers for organizing, and at least yesterday they had an excellent set of speakers. So today, what I'd like to tell you about is my favorite type of finite input-output games, synchronous games. And each synchronous game has a C-star algebra affiliated with it, so that the properties of the game is reflected in the properties of the C-star algebra. So this is a sort of new family of C-star algebras to look at. So today, what I'd like to do is begin by reminding you about quantum correlations. We saw many of these things yesterday, but let me begin there. So suppose that Alice and Bob, so these are two separate experiments going on. They each have n quantum experiments, and each experiment has m possible outcomes. Then the way to describe that, well, so first, I'll let PAB given xy denote the probability that if Alice performs experiment X, Bob performs experiment Y, then Alice gets outcome A and Bob gets outcome B. So there's m squared possible outcomes and n squared possible pairs of experiments they can perform. So there's at least three math models for describing what these kinds of probability densities can look like. And that's what we want to look at to begin with. So the first, most basic model is that Alice and Bob each have a finite dimensional state space which describes the states of their labs. These are two Hilbert spaces. For each experiment, Alice has a projective measurement system. So this is a set of projections which add up to the identity operator as you sum over possible outcomes. And similarly, for each possible experiment Y, Bob would have a set of projections which, as he sums over his possible outcomes, add up to the identity. Then if they share an entangled state, that's just, I'm talking about pure states now, that'll just be some unit vector in this tensor product Hilbert space, then the probability is given by this inner product. You take the tensor product of their two projections acting on the space, and you apply it to the vector and inner product with the vector. So the set of all possible n squared, m squared tuples that you can get that way is what's called the set of quantum correlations or quantum conditional probability densities, just all these possible, sometimes they think of them as matrices, but they really have four indices. And I see I accidentally interchanged things. This one is backwards. The A and the B should be on the other side. Okay. There's a slightly more general model where you don't demand that the Hilbert spaces be finite dimensional, but you just allow arbitrary Hilbert spaces, but you still take a tensor product of everything. And then the most general model, called the quantum commuting model, is you just assume that there's one enormous state space that sort of represents the whole universe. Then their operators, their projection operators act on that space. And the thing that indicates that the labs are separated is that those projection operators should commute. So Cyrilson was the and then it's the same formula. You do EAX, FYB, vector, inner product vector. So Cyrilson was the first one to really examine these sets seriously and study the relations between them. He speculated that they might all be equal. So here's some of the things we know and don't know about these sets so far. So first off, the obvious things, the CQ is the smallest, the spatial is bigger, and the quantum commuting is the biggest of all. It's known that if you do the closure of the two smaller ones, you get the same set, which we usually call CQA for quantum approximable. These are the things that can be approximated. And those states can be identified with states on a certain minimal tensor product of some C-star algebras. I don't want to go into what the C-star algebras are right at this moment. But the main difference is that this CQ, it's closed, and it can be identified with the states on a certain maximal tensor product of the same C-star algebras. So basically asking if these if the maximal and the minimal tensor products are the same, then this CQA and this CQC will be the same sets. And that's what was observed initially by Schultz and Werner, and then in a major paper, Yunga, Nevesquez, Palazuelos, and David Perez Garcia, they showed that if they made this connection between Kahn's embedding conjecture, especially the Kirchberg version of it, which is expressed in terms of min and max tensor products, they showed that that implied, if Kahn was true, then that implied that these sets had to be the same, and also that their matrix-valued versions had to be the same, and in fact that that was equivalent. And then Ozawa later showed that conversely, if you only wanted to look at the ground states, if you knew that for all n and m, then that was implied, those sets being equal implied to the Kahn embedding conjecture was true. So we have this lovely connection that Kahn embedding is the same as studying whether CQA and CQC are the same set for all n and m. And this certainly is a nice, lovely way to look at this. But still, lots of Cyrilson's initial questions were open, and in fact, it wasn't until March of this year, Slofstra gave the first proof that one of these sets, CQ, wasn't closed, so that CQ and CQA are in fact not the same set. His proof is very indirect, though. The fact that we don't even know exactly what the n is for which it holds tells you just exactly how indirect the proof is. It involves a series of reductions, and at each step, you're able to prove that there exists an n, and then there exists a bigger n and a bigger n, but you don't exactly know at the end of all this process what the n you get is, other than you can give some bounds on it. Yesterday in Gao's talk, he said n could be taken to be 200. I think it'd be taken closer to 100, but in any case, it's someplace in that range. But that means the set you're looking at is very large, because it's 100 squared times 8 squared. That's a pretty big dimensional space. And so it's very hard to picture this set at all. So one of the things I want to talk about next week is we have a proof. It's so fresh it's not on the archive yet. We can now show that if you go all the way down to 5 inputs and 2 outputs, that the sets are not closed, the CQ and the CQS. And that's joint with Ken Dykema and one of my thesis students, Jitendra Prakash. So Slofstra's result, one reason he needs much, much larger sizes is instead of looking at the sets directly, he's showing that there's this game that has it's a kind of game called a binary constraint system game, and it has a perfect QA strategy, but no perfect Q strategy. So I'll explain what perfect strategies mean later, but the idea is if the two sets were equal, then anytime you had a perfect strategy of this kind, you'd have to have a perfect strategy of this kind. And so therefore, the Q set and the QA set cannot be equal. So a very indirect proof, but also a very lovely proof. It builds some interesting things. And what we're going to do today, partly, is extend his work a bit. So the outline of what I want to do, first I'm going to go back and tell you a little more clearly what I mean by these finite input-output games. Then I'll tell you about my favorite kinds of games, these synchronous games, and what we mean by a synchronous correlation. Then I'll present some new results about synchronous correlations. We've been working with synchronous correlations for a while, and there was a spot where we were stuck, and we now have a proof. Got us past this one hurdle. And then once we know that, we'll be able to show that Kahn will do a sort of analog of Ozawa's result. That Kahn is equivalent to two sets of synchronous correlations being the same. Then I'll introduce you to this idea of the C-star algebra of a synchronous game. And then we'll construct a synchronous game with a perfect QA strategy, but no perfect Q strategy. And that'll show that the corresponding synchronous sets, QA and Q, are not the same. And from that, we'll be able to construct a graph. There's a lot of theory of quantum graph theoretic parameters, and we'll be able to construct one so that its quantum independence number is strictly smaller than its QA independence number. So I'll explain what all these things mean as we go along. Okay, so first, finite input-output games. So these are games where you have two cooperating players. I'd like to draw the little picture. Sometimes it helps. So the thing to remember is that Alice and Bob are not playing against each other. If they're playing against the referee. So you have Alice, Bob, and a referee. And the referee is going to pose questions to Alice and Bob, and then they're going to give answers. And the referee's either going to like the answers he got to the questions, or he's not going to like the answers he got to the questions. So for each round of the game, the cooperating players each receive an input, the questions X and Y. They each must produce an output, an answer, so that belongs to some output sets. And then there's a rule function, and this is what tells them ahead of time whether they're going to give good answers or not. So the rule function is formally a map from inputs, cross outputs to 0, 1, where if the AB they give in reply to the XY, if the function is 1 there, then that means the referee's happy and they win that round of the game. Whereas if it's 0, that means they lose that round of the game. Okay. So their goal is to cooperate and give a pair of responses so that the lambda function will be 0. So it's this lambda function that gives us all the interesting combinatorics of the game. So they both know exactly what this rule function is, and before the game they can do anything they want to create a strategy for how they're going to play the game, how they're going to try to win. But once the game starts, they have to produce their outputs without knowing what the other person's inputs were. So Alice doesn't know what question Bob was asked, Bob doesn't know what question Alice was asked, but he still has to give an answer. So that's what's meant by this non-communicating. So something is called a deterministic strategy. That would just be a pair of functions. So this means anytime Alice gets X, she's just going to reply with F sub A of X. And anytime Bob gets Y, he's just going to reply with F sub B of Y. So that's what's meant by a deterministic strategy. And it's perfect if it always wins. And you can see that always wins means that the pair of answers that they give would have to satisfy the rule function being equal to 1. So among games, there's these interesting ones that are called synchronous. So in a synchronous game, Alice and Bob are both being asked the same set of questions, And they both have to give the same set of, their answers come from the same sets as well. So one of these we'll look at later is the graph coloring game. So in the graph coloring game, their inputs are a pair of vertices, and their outputs are a pair of colors. And they win the game if any time the vertices are connected, their colors are different. So, you know, when you want to color a graph, adjacent vertices are supposed to get different colors. And then what makes the game synchronous, getting ahead of myself. So we'll let this PABXY represent this probability that when they receive that they give out answers A and B given inputs X and Y. Wait, where did the... Okay, I did say it up there. I forgot to say it. So the one thing that makes a game synchronous is anytime they're asked the same question, they have to give the same answer. That's the synchronous condition. So the things that make a game synchronous are the questions are the same for both of them. The answers have to be the same for both of them. And if they get asked the same question, they have to give the same answer. So if you think back to this graph game I was describing, suppose the referee gives them both the same vertex, then it's natural that they should have to both reply with the same color, or the referee knows there's something fishy. So that's why that would be a synchronous game. Okay. So if the game is synchronous, then if they want to win it always, then anytime they both get asked the same question, they both have to give the same response. So the probability that they give different responses has to be 0. And anytime we have such a density, those are called synchronous densities. And we'll just use a superscript S to denote the subsets of these densities that are synchronous. So we've got synchronous ones in the quantum case, the quantum spatial, the quantum approximate, and the QC case. So synchronous games are kind of a natural kind of game to look at. When they both have the same set of questions, it's natural that they should always have to give the same answer if they get the same question. And so it seemed to us these were a good subsets of the correlations to look at. And the lovely thing is, these are exactly the correlations that come from traces on algebras. So this was proved in a paper with Severini, Stalky, Todorov, Ivan, and Andreas Winter. If you just know that a density satisfies this synchronous condition, then necessarily there's a C-star algebra generated by projections. So if you could just think of these as like Alice's projections, and you can forget Bob's projections in a sense. So they have to sum up to the identity, just like in the original setting. But now to get the correlation of an XY given an A and a B, it's just the trace of the product of the projections. So what we discovered is that in this synchronous case, you can sort of ignore Bob's half of the quantum equation altogether, and all the correlations are given by what happens on Alice's side. And if you look at the functional on the algebra generated by Alice's side, it's a tracial functional. When you look at that state given by that vector, it's a trace on Alice's algebra. Moreover, you can say, so that's if you're in QC, the most general case. You can say what it means to be in Q, and that's that in addition, the algebra has to be a finite dimensional algebra. So the synchronous Q traces are really very limited because there aren't that many finite dimensional algebras and there aren't that many traces on finite dimensional algebras. So the CQ synchronous, so just putting this one condition on really restricts the set a lot more than it seems it should. But at the time, we couldn't figure out what it meant for something to be a QS synchronous or a QA synchronous. So that's the new technical results I want to do today, and then we'll apply those to some games. So the QS synchronous was a big surprise. Allowing yourself tensor products of infinite dimensional Hilbert spaces instead of finite gives you no new elements at all. So that was quite surprising. It relied, so consequently, if you have a synchronous game, saying it has a perfect QS strategy is exactly the same as saying it has a perfect Q strategy. So the proof is really in two parts. The first part is you use the Schmidt decomposition of this vector and this tensor product of infinite dimensional spaces. It allows you to write things as a series of things in the Q set. And then this lovely little fact that I didn't know before, but Andreas told me about, is if you have a convex set, the key thing here is that it's not necessarily closed, and you look at infinite convex combinations, then they're still in the set, even if the set is not closed. And so if you put the two things together, that's how you get this result. So first you get things written as an infinite series, but then infinite series still belong to the same convex set. And so that leaves us with the problem of trying to describe what these QA synchronous things are. They should correspond to some special family of traces on C-star algebras, since QC was an arbitrary trace, Q was a finite dimensional trace. The QA should be some family of traces that lie in between there. And we were finally able to prove that it corresponds to the amenable traces. So let me tell you about amenable traces. So the definition, you start with a C-star subalgebra of B of H. A tracial state on A is called amenable, provided that it can be extended to a state on B of H in such a way that that state is unitarily invariant, but with respect to the unitaries from A. Now, this definition looks like it depends on the particular embedding of A into B of H, but if you use Arvison's extension theorem, you can show if you take a different embedding, then for that other embedding, there would also be such a state rho. So that's the definition of a state being amenable. And then we need Kirchberg's result about amenable traces. So he proved a lovely series of equivalences about amenability. So first, if it's amenable, the first equivalence is that it has this kind of finite approximation. You have CP maps into matrix algebras, which are almost multiplicative. And the thing that's interesting and kind of key here is they're not just almost multiplicative in the regular norm, but they're almost multiplicative in the 2 norm. And such that if you take this matrix representation of A and take its, this is the normalized trace on matrices, that converges to the trace of A as k goes to infinity. So it's this sort of finite approximability. And then the third condition is it's equivalent to if you look at the linear functional on A tensor A op, defined on elementary tensors by A tensor B op, is shipped to the trace of A times B, then that extends to be bounded when you use the minimal tensor product. So we'll use all 3 of these in our proof. And so what our theorem says is if you have something that's synchronous and in QA, then first off, it can be approximated by things which are synchronous and in Q. So 2 implies 1 is obvious, but 1 implies 2 is the rub, right? Because if you know you're in QA, then you know you're approximable by things from Q. But there's no reason a priori that you should be approximable by synchronous things in Q. And that was something Dykema and I posed as the synchronous approximation problem a couple of years ago. And we now know how to solve that. By the way, the K and the S here are Sam Kim, who's a grad student at Waterloo, and Chris Schaffhauser, who's a postdoc at Waterloo. And then the third condition is that just as before, the Pij can be written as the trace of elements in a C-star algebra, but now this trace is an amenable trace. And this C-star FNM is just the universal C-star algebra generated by projections which sum to 1. So if you like, these projections summing to 1, that's a copy of little L infinity sub m, and this is the free product of n copies of that. It can also be thought of as taking the cyclic group of order m, n copies, the free product of n copies of that. That's where this notation up here comes from. So the idea of how the proof goes, I just told you why 2 implies 1 is trivial. So you use 1 to show that the trace that you have is amenable by using the A tensor A op condition. Then you use Kirchberg's equivalence that A tensor A op condition is the same as this approximability by factorization through matrix algebras in the 2 norm, and that's what gives you that 3 implies 2. Okay. But so from that, we get the following, that Kahn's embedding conjecture has an affirmative answer if and only if the synchronous sets are the same, if and only if the regular sets are the same. So 1 implies 3. Keep losing my little red dot. Where'd it go? Anyways, 1 implies 3. That was in the original work by Junge et al. 3 implies 2 is trivial, because if the 2 sets are the same, then the synchronous elements in the sets are the same. And then 2 implies 1. You can do that using Voiculescu's theory of matricial microstates. So what we really have is the matricial microstates are equal for words of order 2. And then if you use the linearization ideas of Collins and Dykema, or Dykema and Yushchenko, it's enough to know it for words of order 2 to get it for all higher order words. So it gives a different route through these things than was in Ozawa's proof that 3 implies 1. Just a little bit. So it's going through the matricial microstates version. Okay, so now finally, let me tell you about the C-star algebra of a synchronous game. So we have this game. It has its inputs, its outputs, and its rule functions. And so by the C-star algebra of the game, we mean the universal C-star algebra, which is generated by a family of projections. You have, they're indexed by each possible input and each possible output. So you'll have n times m projections. And what do they satisfy? Well, just like for projective measurement, these projections should, for each x, as you sum over all the outputs, it should add up to the identity. But then the way the rules of the game show up are anytime the rule function is 0, then the corresponding product of projections is 0. So this is really a C-star algebra with generators and relations, where the relations are given to you by the game. Now, this C-star algebra may not exist. I mean, it could be, if you look at the star algebra and you look at the ideal you need to mod out to make all these things true, then that ideal might contain everything so that the quotient is 0. Yeah, sorry, orthogonal projections. I always mean orthogonal here. So you have mutually orthogonal projections adding up to 1. And so, what is this C-star algebra good for? Well, if you have a synchronous game, then it has a deterministic strategy, a perfect deterministic strategy, exactly when this C-star algebra has a one-dimensional representation. So in the case of this graph coloring game, we were able to characterize the chromatic number in terms of whether or not a C-star algebra had an abelian representation. For Q strategies, it's exactly when this algebra has a non-trivial finite dimensional representation. And for QC strategies, it's exactly when this C-star algebra has a trace. And now we can add on the QA strategies. It's exactly when it has a hyperlinear trace. There's a parallel theory to amenable traces for hyperlinear, but basically hyperlinear are the traces for which Kahn embedding is true. So a trace is hyperlinear if A comma tau can be embedded into the, in a trace-preserving manner into the ultra power of the hyperfinite factor. So now I haven't really told you about many games yet, so now let me start with a new game, which is the synchronous BCS game. So all of Slofstra's work was built around these BCS games. Because I like to do everything in a synchronous manner, we'd like a different version of Slofstra's game that's synchronous. And I think the synchronous game actually captures what BCS games were all about in the first place a little better. So let me tell you what the synchronous BCS game is and what the BCS game is. So in both of them, you're starting with a system of linear equations over Z2. So you've got some M by N matrix, and you'd like to try to solve AX equals B. And the idea of the game is that Alice and Bob, you want to play a game so that Alice and Bob convince a referee that they have a solution to the equation. Now, the game turns out to be boring if there actually is a solution, because if there is a solution, then that's when there's a deterministic strategy, and their answers are just to keep giving information about the vector x that is the solution. But it's interesting when there's not a solution. But so how are you going to make a game that allows them to convince a referee that they've solved this system of equations? So the idea is to imagine that M is very, very large, right? So you don't want to just write down the whole set of equations. Or maybe the referee doesn't even know yet what the entries of the rest of the matrix are. It's something like a Netflix problem where the entries are determined as you're going along, but you want to convince people you've solved the problem. So, well, first off, if you did have a solution, then if you looked at the ith row of the matrix, in order to solve that equation, the ith row dot producted with x would have to give you the number b sub I. So here's the way the game goes. The referee chooses a pair of rows, I and j. Unfortunately, j is going to stand for a row for the moment. And he gives Alice, tells her that she's got row I, and Bob that he's got row j. And now they each produce an output vector, something that could be plugged into this equation. And then they win if, well, first off, he knows something is fishy if he gave them both the same row equation to solve and they gave different answers. So there's the synchronous condition again, being very natural for this game. And also, they've got to at least solve their equation. And then the last condition is that anytime you had, if you think about solving this equation for a moment, anytime the entries of a row are 0, it doesn't matter what replies people give, because those won't affect how things sum up, whether they sum up to the values of the vector x only matter where aix is non-zero. So whenever you have a k so that aik is non-zero and ajk is non-zero. Oh, I'm sorry. If these are zero, then the entries don't matter, so they might as well be set equal to 0. Getting ahead of myself. And then the last thing is, if you have entries that matter, namely if aik is non-zero and ajk is non-zero, then the entries that Alice used for her solution and the entry that Bob used for his solution better be the same number. Okay? And so that's the way that you convince the referee you've solved this system of equations. It might be very, very large, but there might be only, say, 3 non-zero entries in the row, and then Alice only has to reply to what she's going to do for those 3 non-zero entries, and Bob only needs to reply for what he does for his non-zero entries. And anytime they have a non-zero entry in the same location, they have to give the same answers. Now, the way the original BCS game goes is Alice is given a row, and she gives a vector, and Bob is given a column, and he just gives a single element of Z2, and his element of Z2 has to agree with Alice's vector in that spot. So that's the BCS game. This sync BCS game, I think, is a... Pardon?
So if it is that final, the winning strategy is not responding X, right? But to zero out X is appropriate?
Yeah, right. You zero out X is appropriate. But the key thing is the other entries don't matter, really. Yeah. Okay. So here's what we can say about this sync BCS game. So first off, we still need to use Slofster's construction, and it gives you this matrix A of some very large size. But for that matrix A that came out of Slofster's construction, and the vector B that comes out of Slofster's construction, if you now look at the sync BCS game, then it has a perfect QA strategy, but no perfect QS strategy. So exactly the same thing Slofster got, but now for a slightly different game. And now the point is that the strategies have to be synchronous strategies. So that tells us that the synchronous sets can't be equal for the QS and the QA. And the number of outputs is, you really only care about how many entries there are in each row that are non-zero. So it's really 2 to the k, where k is the number of non-zero entries in a row. So it's very similar to Slofster's result, but it's a little stronger because if the Q sets are not closed, that doesn't mean that the QS sets are not closed. But if the QS sets are not closed, then that guarantees that the Q sets are not closed. So it implies Slofster's result, but working with this other game. And yeah, that's the moreover. Since the synchronous subsets are not closed, the bigger sets cannot be closed. Okay. In the last few minutes, I'd like to tell you about graph homomorphisms in some of these graph coloring games. This is what I want to do in my lectures next week, so maybe I'll go through it. Given that I have 5 minutes, maybe I'll go through it a bit quickly. So the idea of graph homomorphisms, you have a graph with a vertex set and edge set, and a second one with vertex set and edge set. Then a graph homomorphism is just a mapping from the vertices of G to the vertices of H that satisfies the following property. Whenever a pair is an edge in G, then their image must be an edge in H. Now, graph homomorphisms are, so they just write G arrow H to indicate there is a graph homomorphism. they're a very handy way for doing a lot of graph theory, because most graph parameters that you look at are really defined by these. So for example, if you want the chromatic number of a graph, it's just the smallest c, so that there's a graph homomorphism from G to the complete graph on C vertices. Because anytime you have such a morphism, if vertices are adjacent, they have to go, well, the only vertices that aren't adjacent is if they're identical. So whenever V and W are adjacent, they have to go to different vertices, and that means they're going to different colors. And so a homomorphism is the same as a coloring. The clique number is just is the largest C, so that you have a complete subgraph of size C, but that just means you can embed a complete graph of order C into G. And the independence number is just the largest set of vertices which have no edges, but if they have no edges, then in the complement of the graph, they're a clique. And so the independence number is also defined by graph homomorphisms. And now the point is, graph homomorphisms is something you can make a nice game out of. So the graph homomorphism game, you're given these two graphs, and the game goes as follows. The inputs for Alice and Bob are vertices of G, and they must output vertices of H. And the rules are simply that, well, anytime they're given the same vertex, to convince the referee they're not fooling around, they better reply with the same vertex from H. And whenever they're given adjacent vertices from G, they have to reply with adjacent vertices from H. So we say that there's a quantum homomorphism between two graphs, either a Q or a quantum approximate or a quantum commuting, provided that there's a probability density that would win this game with probability 1. So that just means that anytime something is disallowed, the probability of that outcome has to be 0. So you can write down exactly the conditions on this probability density you need and the particular pattern of zeros that have to emerge. And then once you have a notion of quantum graph homomorphisms, you can define all these graph parameters have quantum versions. So for example, the quantum clique number of a graph is just the largest C for which you can win the graph homomorphism game from KC to G with probability 1 using a probability density that comes from the corresponding set. So T just tells us which kind of set we're looking at. C sub Q, C sub QA, and so on. And independence numbers are defined by just using the complement of the graph, and chromatic numbers are defined similarly, quantum chromatic numbers. And so what we've been able to show is that there exists a graph for which the quantum clique number is smaller than the quantum QA clique number. It's a graph on about 100 vertices, coming again from Slofstra's construction. And what this means exactly, if you look at the C, which is equal to omega QA, then you can win that game with probability 1 using something which is a quantum approximate. And that means that, that for every epsilon bigger than 0, if you try to win it with a quantum probability density, there is one that wins with probability 1 minus epsilon, but there isn't one that wins with probability 1. That's because the QA synchronous is the closure of the Q synchronous. So once you take this one in QA that wins with probability 1, you can approximate it. So to build this graph, we borrowed heavily from a paper by Asterius, Mansinska, Roberson, Samal, Severini, and Vervetsiotis. And basically, they show how to start with a BCS game and build a corresponding graph if and only if the BCS game has a perfect Q strategy. We just needed to extend their proofs to the QA and the QC, which was quite easy to do. We just had to copy line by line their proof in the Q case and show it worked in these other two cases as well. And yeah, so what I just said is there. And then again, we use Slofstra's game to get the BCS game that does all this for us. Well, that's all I had to say, and here's the references.